write on top, and then you repeat. Okay, so at some point you stop. That's a snake graph. It's a graph. I mean, each tile is a 4-vertex graph and 4-edge graph, and then you just glue them all together like this. Okay, I will denote them by these fancy G's, and then there's another construction, the band graph. And sometimes make a little circle there. Sometimes I make an overline because it's not always the same way to construct them. But a band graph is obtained from a snake graph by identifying one of these edges here on the very front, the south or the west edge, with the north or the east edge of the last tile. Actually, I'm a little vague here. If you choose one edge here, then its partner will be determined by that choice. It's not completely free. I'll get to that later again. So you take your snake graph and you do this. Is like a snake biting its own tail, if you want. I thought I saw this picture somewhere here in this room. Yeah, anyway. Ouroboros. Ouroboros. Yes. And then we'll write match G for the set of perfect matchings of G, and now you might think you know what this is, but I must surprise you a little bit. These are the perfect matchings of G which restrict to perfect matchings of G circle. So, right, so I write here the same as I have written above, but then I continue that restrict to perfect matchings of the band graph. And so, for example, if this is G, and you glue the left edge to the rightmost edge, which I like to indicate by putting some dots. This point is actually identified with that one, and then of course the edges between the two dots are identified. So then on top, I can draw this matching here. That's a perfect matching, but it doesn't restrict to the graph here because this point here and this point are the same point. It will be covered twice. So this. Okay. So yes, so the question is, should they contain the gluing edge? Yes, Not well. Well. So if they contain the gluing edge twice, you are allowed to drop it. No, I'm not. I don't think they have to contain the gluing edge. In this example, yes.
H, then there's another H. And after glue, we get logics of the grid.
Yes, or maybe yes. Okay, so the motivation here comes from cluster algebras. So these graphs they are used in cluster algebras from surfaces to construct a canonical basis. Yeah, this is work with Greg and Laurent. Some time ago. So you get expansion formulas for the basis elements who are parametrized by the perfect matchings of these graphs. Okay, so a little later, we discovered with Ilke Chanakshi that there's a relation to continued fractions. Usually I would say there's a combinatorial interpretation, but now I'm kind of afraid of saying that. So there's a relation to continued fractions. So take a continued fraction, a1, a2, up to an. So this is a1 plus 1 over a2, and so on. And we want the AIs to be positive. And you can associate a snake graph to it. Which I then denote like this. How does this go? So in this graph, there are interior edges, and I will also add one edge from the beginning and one edge at the very end. So I have two more edges than all the interior edges. So I'll put plus and minus signs on them. So you have three interior edges plus one on the boundary. This one I chose. I could have chosen this one. I want this one. And then you see they all lie on the same diagonal line here, these edges. And then the next one doesn't anymore. So I switch from minus to plus. And then here I have to switch again. And then I have a choice again. I'll choose this one to make it not so complicated. And so you have minus, 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 minus. That was 4 of them. Plus, 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 3 pluses and 2 minuses. And that's your continued fraction. So there's kind of a bijection, but there's this ambiguity at the end. You choose this one or that one. This would be a 2 or a 1, 1 at the end, which doesn't make a difference for the continued fraction also. So you can think of it as really the same, continued fractions and snake graphs. That was related to this joke with about the, yeah. The question was if the back of my t-shirt was related to the graphs. Okay, so I mean, so far I didn't say why this is not a relation to number sequences, but so the theorem here is that the number of perfect matchings is exactly equal to the numerator, which I just abbreviate by n, of this continued fraction. Or if you prefer, it's the continuum polynomial. So then, 2 years ago, I thought one good open problem would be to generalize this correspondence to, or to extend it to band graphs. But this is not open anymore. Yeah, not open. Actually, that's solved by my student, PJ Abruzzese. Yeah, so he says you take the band graph and you associate a periodic continued fraction. So this is an infinite continued fraction, which has period, well, some sequence there. And now these are really all interior edges. Right there, and for the snake graph, we had some boundary edges, but now we are gluing. And now these are just exactly the interior edges. So right. And then the number of matchings so this can be given in 2 ways. So this is a continued fraction which is periodic if you compute its value. So it's still defined like this. It's just, it doesn't stop. If you compute its value, you will get a quadratic irrational. So this will be of the form a plus root d over b. And all quadratic irrationals are of this form. Well, maybe there's something here before the period, but yes, and the number of matchings will be the root of d plus 4. Which is kind of surprising that somehow you get a radical formula for the number of perfect matchings. And this is a little imprecise. I have to. So sometimes you can simplify this expression, right? You do some computation, you get this formula, and then you see that, well, B and D have some common factor. You can simplify, and then of course this changes. You don't want to simplify. So this is equal if you compute it the right way. Yes. Yes, that's what I said. When you choose the first edge, the last one is determined, has to have the same sign.
a nice example of just like Fibonacci numbers. Just a row,
That's right.
This is just
Exactly. That's right. Yeah, so the question was if you have a horizontal snake graph, if the number of perfect matching is Fibonacci numbers. That's right, because the continued fraction will just have ones. That's right. Exactly right. And so there's a, to make it exactly precise here, you can write it as a trace formula of a 2x2 matrix, which is this 2x2 matrix you usually associate to a continued fraction, PQRS. Yeah, I don't want to erase that. Here, each of these PQRS are numerators of continued fractions, of finite continued fractions. P is the numerator of this one. You just forget about the period. And then Q, you drop the first, instead of starting at A1, you start at A2. R, you drop the last. And PQRS, you drop the first and the last. Yeah, so with this formulation, the number of matchings is just P plus S. So for example, well, let's do 2, 2 first. This is a snake graph, which looks like this. If you compute this continued fraction, this is 5/2, and the snake graph has 5 perfect matchings. And if you do the corresponding band graph, so now corresponding doesn't mean take this one in blue. You see, this edge here, this very first minus edge and the last minus edge, these are the ones that I'm gluing. And then if you look just at interior edges, then the sequence is exactly what I've written above, 2, 2, and then it will repeat. Okay, so then you want to compute how many matchings do you have? Well, you take this continued fraction without the bar. I computed it over there. It gives you 5. And then you remove the first and the last, an empty continued fraction, which gives you 1. So here you have 6 perfect matchings. Say again, I didn't hear you. That's right. Yes. So the question is, what if I choose the other edge to glue? So if I would use this one instead, this would be then a plus edge. And I would have to use that as well. The plus edge at the end. So I'm gluing this way. The continued fraction will change. This is 3, 1. And yeah, the number of perfect matchings is also not the same. Well, both compute the same thing. The question was, how do these formulas relate to Castellan's formulas? So the Castellan formula is a determinantal formula to compute the number of perfect matchings. Yeah, I don't know. Yes.
So you're not the perfect matching of G, so not very. It's not just matchings of the periodic graph. If you take the periodic fraction, it matters where you break the period, right? For the continued fraction as well as for the graph.
Continued fraction changes, but not its radical. The formula for the matchings only uses the D. It doesn't use A and B. If you cut this somewhere else, A and B will change, but not the D.
Okay, but then for the graph, then your notion should also be there.
It is, yes. I could have written 1-3 instead of 3-1. This gives you a quadratic irrational, this continued fraction 3-1. And if you write 1-3, it will give you a different quadratic irrational. But the radical in both quadratic irrationals is the same. And the D is the number under the radical. No, that's what I said earlier. You do not want to simplify it. So if you really want an exact expression, it's best to think of it like this. But if you write out the continued fraction and then you write, if it's periodic, you would have 1 over alpha here. You can multiply with alpha, you get a quadratic equation. And then you just use the quadratic formula. There's a D under the square root, and it's that D without any further simplification.
One way to get that is to take a linking diagram of type A or of one type with arrows. I'm just guessing. So linking diagram is kind of fusion.
Yes, it's related. Yes, it's. So the question is, is this strongly related to type A Dinkin diagrams and quivers of type A? And the answer is yes, it's strongly related. So the perfect matchings, you can associate a representation of a quiver, and the perfect matchings is the submodules of sub-representations of that representation. Second question was, can you do it for other Dinkin diagrams? And the answer is, I don't know. This is one of the open problems I wanted to present. No, no, it's a good open problem. Yes?
Then these matches like domino tiles and these pluses and minuses it's like two portions.
So the question was, is there a connection, a deeper connection to skew Young diagrams? And the answer is, I don't know. So since PJ has solved this problem, the open problem now, I could ask for, what about double dimers? Or double perfect matching? As we saw in Rick Kenyon's talk, they have recently been shown to do this, what these snake graphs did. Well, it's the same snake graph, but instead of, if you use double dimers, then this is related to super cluster algebras. in recent work by Musiker, Nick Ovenhouse, Sylvester Zhang. And so you can ask, can you modify the continued fraction so that you get something that counts double dimer covers of the snake graph? And this is actually a problem one can do, I think. Not so sure about the other ones that I'm going to present. Not all of them. So I need to make a digression now into number theory. And I will talk a little bit about the Lagrange spectrum. And to do that, first I will talk about Markov numbers. Okay, so a triple ABC, these are positive integers, is called a Markov triple. If a square plus b square plus c square is equal to 3abc. That's the Markov equation. And here are some examples of these triples. So you can very fast check that 1, 1, 1 is the solution to that equation. And then 1, 1, 2 is 1, 1, 2, 5. Okay, so now we have to go a little bit slower maybe, but I don't want to. So the point here is, except for these first two, once you have a triple, you can construct 3 others by something that's called mutation. And this is coming from cluster algebra. So this is mutation in the cluster algebra of the Markov quiver. That already came up in Sergei's talk. Okay, so these are Markov triples. All the numbers that appear, any of these numbers that appear in some Markov triple, these are called the Markov numbers. And Markov introduced them over 100 years ago in the context with approximation theory. And well, before I go there, let me state a famous conjecture by Frobenius, the uniqueness conjecture. Which says every Markov number is the maximum of a unique Markov triple. And the important word here is unique. So the rest is known. And not only this is open since a long time, but a lot of people have worked on this with a lot of different approaches. Don't work on this unless you have a really new idea. If you're not sure about whether your idea is new or not, then there's a book which gives an overview. Which was written exactly 100 years later. So in 2020, well, published in 2013, and it's called 100 Years of Uniqueness Conjecture by Eigner. So it's related to many areas in mathematics. And now I want to talk about Lagrange spectrum. So let me talk about Lagrange numbers. So you take alpha, any irrational, and then its Lagrange number is the soup of all real numbers L, such that there exists infinitely many rational numbers such that, well, it's about approximating alpha by rational numbers. So I take the distance between alpha and the rational number, and I want it to be a good approximation. And how do you measure it to be a good approximation? You want it to be smaller than 1 over the square of the denominator. And that's not enough. You have to put the L there somewhere, and goes right here. So if you keep L equal to 1, you can always do this. So the question is, you want to really squeeze out the best possible way to approximate. So you want to know what is the maximal constant that you can put here, such that you still have infinitely many P over Q that approximate your number. And so this depends on the real number alpha that you start with. And so you can associate this L of alpha to it. It's the Lagrange number. And in a way, it measures how well can you approximate your number by rational numbers. And then you take all of these L alpha, and this is called the Lagrange spectrum. And this is a very fascinating set. So it lives on the real line. Here's the real line. And then somewhere, maybe exactly where the separation here is the number 3. And then somewhere over here is the Freiman number. Which is approximately 4.5 and so on. And then this spectrum is continuous once you're on the right-hand side of this Freiman number. So past this point, every number is a Lagrange number. It is discrete before you come to 3. The smallest here is square root of 5. Then you have square root of 8. And then, well, there's many other things, and it converges. Well, 3 is an accumulation point. And between these two, it's fractal. And I think people, we do not really understand what it looks like. There are some things which are known. There are some intervals here which are really empty, and some others where you have accumulation points. And now, so Markov was interested in that, and let me write down his theorem. 1879, this discrete part of the Lagrange spectrum, so the part which is smaller than 3, is equal to, you take the root of 9m squared minus 4, divide by m, where m runs over all Markov numbers. So for m equal 1, you get the square root of 5. For m equal 2, you get the square root of 8. For m equal 5, you get the square root of 221 over 5. And then it continues. That last one I named is already over 2.9, and then all the others, they squeeze in there somewhere. Okay, that was my little excursion into number theory. Any questions here? Well, yes. Huh? The question was if this 2m squared minus 4 was related to the d plus 4 that I've used earlier. And the answer is yes, it's related. And I think we'll see a little bit of that. Okay, good. So now let's go back to combinatorics. So I will consider now a class of snake graphs, which I like to call lattice path snake graphs. Maybe dick path snake graph would be a better word, but I don't know. So it's part 3, I guess. Okay, so I denote by AB a point, a lattice point. I want B to be smaller than A. I want B and A both positive. I want the GCD of the two to be 1. And then I take D of AB is the set of all dick paths. From the origin to AB. So these have come up in several talks already. So you start at 0, 0, and you take, it's a lattice path, and you're only allowed to go right or up. And you always have to stay below the diagonal. That's what I need. And then for any such path, oh, sorry, I also need, sometimes I will need this D, which is the union of all these DABs. And for any path W, we associate so it should be probably 2. We associate snake graph and a band graph. And the band graph I'll write with a bar now, because I think of it as a periodic continuous fraction. And well, as follows. I will show you an example, and that should make it clear. Okay, so I want to go right 3 times, then twice up, and right and up. And let me do the same thing here. And here I'll put the snake graph. And here I put the band graph. Is it clear? So you put boxes which have side length 1/2. You put them along your lattice path, and you remove the very first and the very last. Right, so you start with the snake graph such that this is the southeast boundary, and then you remove the first and the last tile. This is the snake graph. And this is the band graph. Well, you see what's happening. I put in the first tile, I add in 2 tiles at the end, and then I glue. So another way of thinking about this is you take your lattice path and then you repeat it, and you repeat it, and you repeat it, and then the covering of your band graph will just be the graph that sits on top of this lattice path. Is this clear, or should I write down the construction? It's okay? Question?
Just to make sure I'm understanding this, if our lattice path ended with the right step, this final box we're adding still goes on top.
We always end in a vertical step because we have the condition that we stay below the diagonal.
Right.
And also the first step is always horizontal.
Right.
There was another question, yes? You're worried that this point is above the diagonal? No, because there's more horizontal steps than vertical steps. Other questions? Okay. The race against time. Okay, so, right, so we also know how to describe these things with continued fractions. So here we have right, up, right, up. And then there are commas here between these letters. This is the path W. And now I replace the comma by numbers. I put a 1, 1 if the letter before and after are the same. Here another 1, 1. I put a 2 if there's a change in the letters. Here U and U is the same letter. UR is a change. RU a change. And that's the continued fraction of this snake graph. And I will write this as usual as A1 to AN. And so to construct this one, you just prepend a 2. Because you were already done up to here, and then here you get a 2, which I just write in the front. Okay, so for every lattice path, we have 2 graphs. And now we will associate numbers. And we'll define an order, 2 orders really. So first, right, so this GW is still this thing here, this continued fraction A1 through AN. Then I'll define M of W to be the number of matchings of GW. And if you remember from earlier, this is the numerator of this continued fraction. And I'll define L of W to be the Lagrange number of the periodic continued fraction of the band graph. Right, so this is not the number of perfect matchings. This is a quadratic irrational number. Right, and then you can define an order the matching order is an order on the lattice paths and a partial order. And you can define its Lagrange order as well. So you get two posets. And so my proposal is that we study these posets. Say again, please. That could be the case. Yes, that's right. The question was if there could be paths which have the same M or the same L value. And we'll see more about that. So let me first, before coming to the open problems, let me tell you what we know. There's a special Dick path, which is the Christoffel path, which is the path that is closest to the diagonal. And yeah, Coxeter people will not like this, but I will denote it by W0. This is the unique minimal element, so the unique minimal element for the set of big paths with a matching order. This follows from work with Kyung-Yong Lee, Li Li, Michel Rabidou. And if you evaluate M on this path, you get the Markov number. Yeah, this was, if you think about the continued fraction, this was already known to Frobenius. If you think of it as a cluster algebra, then this was first observed by Prop, that these graphs give the Markov numbers. And if you like this particular set of how to construct this, then it's Chanakshi and me.
You get all Markov numbers?
Yes, all Markov numbers. Yeah, so yes, the question was if you get all Markov numbers, the answer is yes, because you get them all in the cluster algebra of the Markov quiver, and these correspond to geodesics on the one punctured torus, and these are all these lines with relatively prime slope. So first I thought I write here also the other order, but I'm not so sure. So maybe also so I think minimal is okay. You need, well, so I better not say anything exactly. So what I know is if you take the continued fraction that is written there and you evaluate, well, to do the Lagrange number, you have to consider all cyclic shifts of this one. But if you just take the one as it is written there, then this L of W0 will give you the same number as in Markov's theorem, where M is this Markov number that you get from M of W0. So this is a number that's below 3, and which is why I think this should be smallest. If you do a cyclic shift, I don't think you can get smaller than this one. And so it also should be, I also think it should be the smallest because it's very unlikely that you find something below 3 in a different way. It's the Lagrange number of the continued fraction of the band graph. Right, you have continued fraction of the snake graph, you put a 2 in front, you take the periodic, and then you compute the Lagrange number. So I think having these two statements means that we have exactly the right graphs. You get the Markov number, you get Lagrange, you get Markov's theorem. So it makes sense to study these posets. And now I get to the list of open problems. Okay, so first, the unique minimal, sorry, that was minimal, the unique maximal element should be the path, in D, AB, should be the path that goes all the way to the right and then up. So this would go right, A times and then up B times. For both. Thanks.
So your next conjecture of one of these is and then there's a process of dick path, right?
I did not hear you.
The dick paths have a process structure that's for all. This is a linear extension of that.
I don't know. Good question. So the question is if, right. It's a good question. So the question was if this order here is compatible with the natural order on the partial order on the dick paths just by being below the other one. And I think that's true. I could write that as well, yes. So question 2, so these are, I write this as statements, but these are questions. So maybe I should say, do we have consider the Christoffel path in AB, and then you consider the Christoffel path in A prime, B prime, if and only if AB is A prime, B prime. Second, same question for L. And part A is equivalent to the uniqueness conjecture. So maybe you don't want to try to solve this, but maybe you want to. And this is kind of a new approach here, but I don't know if that helps you. And part B, well, part B implies a uniqueness conjecture, but probably also equivalent to it. Three. So take two paths, both going to AB. Then is it true that, right, so do we have is MW the same as MW prime if and only if W is equal to W prime? And that's a nice question. The answer is no. Sorry, it's not an open problem. So you use a computer, you let it run a little bit, and it finds a counterexample to that very soon. So you could ask instead, if these numbers are the same, can you say something, can you characterize it in terms of the paths when these numbers will be the same? And then you take the analog question for the Lagrange numbers. But here you do not want to ask this because you really want to ask if when these associated band graphs are not the same but isomorphic. So you have to, if they are the same up to a cyclic shift or up to a reflection, then you will get the same Lagrange number automatically. So it's a little different. This one is open. My program didn't let it run for so long time, but at least in small cases, there doesn't seem to be a counterexample. You could ask if one is smaller than the other, then well, anyway, how do these two orders relate? Okay, 5 is the Lagrange number smaller than 3 if and only if W is a Christoffel path. In one direction we know, but the other one is open. 6, conjecture is that the maximum, well, the soup of all the LWs, here W really runs over all paths, not limited to the endpoint. So the endpoint also varies. Is 1 plus square root 5. I erased my Lagrange spectrum. So here it comes again. So there was square root 5 is the smallest number. We obtained that. Then there's here the 3, and 1 plus square root 5 is not very far beyond 3. And so the kind of the conjecture is that here you get here only if you have a Christoffel path, and after that you always lie here. And so the question 7, well, here you get everything. Question 7 is what part of this interval do you get? Right, so of this part of L, you do not get 3 because the numbers that we construct are irrational. But you can ask what you get after 3. And then, well, relating it to other talks, what is the relation to these other statistics like area or DINF? Or Frank's question, just is there a name for your partial order? Just being below. Yeah, so these we have seen in Pavel's talk yesterday. This is QT Catalan statistics. Okay, so this is all I have. So I don't know. I haven't thought about these problems very much. So I'm not sure which one of them are feasible. Well, I know which ones are probably very hard. I mean, the big hope would be that you, instead of looking just at the Markov number, now you have some big set of paths. Maybe you can characterize the paths that give you Markov numbers, and then I don't know, maybe this gives a way to approach uniqueness, but that would be very optimistic to think that. So thank you very much.
Thank you, Ralf, for the interesting talk. Are there any questions or comments? There we go.
Yes, for the band graph. The question was, if you have this continued fraction for the band graph, how do you compute the denominator of the quadratic irrational? I mean, for whenever you have a periodic continued fraction, this is the same as, well, this is the same as A1, AN, alpha. And now it's just like a finite continued fraction. And then the denominator is when you drop this. But I mean, what you would do is you write this, you know, there's this recursive formulas where you have you pull out the last one, and then in the second term you pull out the previous one as well. And then you divide by the same thing, but starting with A2. These are exactly these PQRS I have written earlier on the board. And then you multiply, and then you get a quadratic equation in alpha. And then, well, one of these is the denominator. This one, I think.
Any more question?
Yes. The relation between D and L? Right. I shouldn't have, right? Yeah, sorry. I mean, if you do this computation, I think then it becomes clear. I would have to look in my notes so that the question was, here you have 9m squared minus 4, and in this previous formula for the number of perfect matchings, we had square root of d plus 4. So here, if you add 4, for example, you get an integer, right, when you take the square root. And this happens also with the d. And yeah, there's a reason for it, which lies in the quadratic formula and in this fraction here. But one would have to compute it, then you see what happens exactly.
So what's the Lagrange number of voting question?
Square root 5. Yes. That's the first, yes. The second is the square root of the silver ratio, the continued fraction only 2's. And then the next one is 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, 1. So about the question was, is there any hope to use cluster algebras to say anything about these questions? It depends on what you mean by anything. So if you are thinking about solving the uniqueness conjecture, then people have thought about this. I think many people in this room. And that doesn't mean there's no hope, but it is not obvious, at least. You can use cluster algebras to get a handle on the order that you find in the Markov number. So each point in the plane gives you a Markov number, and you can ask, if you go along this line of slope -1, for example, do the Markov numbers increase or decrease? And this is known for lines of certain slope. So it is it's exactly known up to which slope you can go and it's still decreasing, and up to which slope you can go and it's still increasing. But then there's a gray area where it's not increasing along lines, so that's why you don't know uniqueness. But these results were proved using cluster algebras.
Okay, if there's no more questions, I thank Ralf again.